Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. In the last class, we talked about various governing equations for a few class of problems, such as a one-dimensional dot string with a lateral application of the load, and which we extended it to a membrane problem, a two-dimensional membrane problem, where the membrane is under tension with some T, and then there's a lateral load which leads to deflection. So this is a simple application of 1D to 2D, and which led to the Poisson's equation. Then we also said that the same type of equation will come in the case of a torsion of non-circular cross-section analysis. And then let's now move on to another important application here, is regarding the heat conduction problem. In the heat conduction problem, can also be 1D and 2D and 3D, but let's take the case of a 2D in the sense that we have a plate here in 2D with some domain omega and boundary omega gamma here, and then this is subjected to certain temperatures here as well as certain heat flux input. So in this case, what happens is that at any point P here with coordinate xy, so there is a temperature which is a function of xy. So let there be a temperature here. The temperature so this is the variable which we represent by phi, and in particular here, which is a function of temperature. This is at P, at a general point P. So we have phi as a function of xy here, and then which is which keeps changing from point to point depending upon the conditions here. In fact, the geometry is defined by the domain omega and boundary by gamma here, and then this has certain properties here, material properties, which is the conductivity, which we represent K, the conductivity of this one. And also let's assume that that the plate is of uniform thickness, throughout the domain omega, thickness T. And then obviously there is boundary conditions here, and on the boundary there can be heat flux input, and then some part of the boundary also may be maintained at some other temperature, a constant temperature or a variable temperature. So here, this is as far as the domain is concerned. As far as the variables are concerned here, this is how we do. So let's try to derive the governing equation about that governs the variation of phi within this one. So, and we'll come back to the boundary conditions a little later. But right now, first of all, let us see here is that at any point P here, let's just take a small there, just around P. So let's take a small elemental volume here and delta X and delta Y here. And then there is a heat going in here and heat leaving here, right? Okay. So the heat going here represented the heat flux, we represented by Q here, and then Q here. On this side, let's say we'll put a subscript X here and QX, and here delta QX. So this is in the X direction. So similarly in the Y direction, we have heat going in QY and QY here, delta QY. So this heat flux going in. And then apart from this, we also have some heat coming from inside. Imagine that there are some electrical conductors which are embedded here, so which takes the energy, heat energy from electric current flowing, and then that may be input into this one. So there may be a so there can be heat generated here or heat input from external sources, let us say Q at this point, and the Q by itself may be a function of XY. So that means that how much heat is input in this one, and this Q also is heat input density. So it's per unit volume. Okay, so this is how the thing is that. And then there another thing here, the heat flow here, Qx, is related to Q here, for example, is related to minus K dou phi by dou x. So what it means is that the heat flow rate depends upon the conductivity of the material, and then this rate of temperature, the derivative of the temperature in the x direction, and then this negative sign is because heat flows in the negative direction of the slope of the temperature. So that means that it goes in the opposite direction of the temperature gradient. Okay, so that's how the Qx is, and so similarly Qy is so where K is the conductivity of the thermal conductivity, this is the thermal conductivity, because of course there is also electrical conductivity, so we say thermal conductivity. So this is various terms that are involved here, and then so to make a heat balance here, so this is here heat going in and this is heat going out. So we take heat leaving this particular volume, representative volume, we'll take it to be positive, and this we take it to be negative. So equilibrium heat is that, so we take it to be minus Qx, and then this is the density. Qx is per unit area, so multiplied by delta y and thickness T. T is in the other direction, and then on this side we have 2x, same thing as this one. Okay, so this is heat going into the representative volume. So heat leaving, we will take it to be positive, and this is negative. And so similarly here, in the y direction, we have Qy delta x times T with a negative sign, and so this is as far as the heat going through the interfaces. And apart from this, we also have, so we have Q, we have, this is the heat coming from external sources. So this is also entering the system, entering this representative volume. So we'll take it as negative and multiplied by T. So this is equal to 0. So this is the total balance of heat. Okay, so you can subtract this one. So what we have here, and into delta y, and I cancel this Qy with this Qy, and minus Q. I cancel T also. T is the uniform thickness. So this is how it is. Okay, and then we have delta x, delta y here, and we cancel with delta y one of it, and we have it delta y here, and then this is in the limit. You can change it to d into the derivatives. Fine. So this looks like this one, and this is using the heat flux Qx and Qy. So as we said here, the Qx, we can write it as minus k dou phi by dou x. So that means that here minus k and in fact here we have to make use of the derivatives here in the partial derivatives, because in the we'll change it to partial derivatives here. So now we have written it is as a total derivative d here in the x direction. So once we write it in the temperature phi, so since phi has a derivative both in x and y, so that is why we convert that into x and y. So this is how, so coming back, so let's continue that equation. So we can write it as dou x of so I cancel that negative sign. So this is at any point P, this equation has to be valid. In fact, here the thermal conductivity right now is within the bracket here. So which means that this equation is valid even when the thermal conductivity K is a function of space xy. So that means that the body can have different conductivity values at various domains, and that can be taken into this one. So that can be included K as a function of xy. But on the other hand, so if K is constant, so what we can write is that K can be taken here. We can write it in this manner, in omega, or we can take it so we can even write this one as del square phi is equal to minus q by k. So you can write it in this manner also. This is a Laplacian operator, and you can write it in this manner also, where the delta square here okay. So this is anywhere in omega, and so you can see here that this equation is nothing but your Poisson's equation. So this Poisson's equation, as you can recall, we also have got it earlier in the case of membrane, and I also mentioned that such examples are equally valid for a torsion of non-circular cross section. So this is a governing equation which is valid at every point in the body. And now let's look at the boundary conditions. What are the various boundary conditions that are possible for this kind of heat conduction problem? So the boundary conditions are so the boundary conditions here are, let me just draw a little bit bigger because we have different types of boundary conditions. All right, so here we have the governing equation in the domain omega, and then we have the boundary, which we call it as gamma. And there are different types of boundary conditions here that are possible. One is the application of the temperature. So that means a part of this boundary can be maintained at phi is defined here. So phi is equal to phi bar is defined temperature. So this temperature is given by the user, which is defined to be a phi bar. So anything that's shown as bar here is denoting that it's a defined value. So this is phi is equal to phi bar is defined temperature on a certain part of the boundary here. For example, in the boundary, let's call this as over A and B. So we have a boundary. So this is just for the sake of over AB. So this is of course arbitrary. AB can be at the top, at the bottom, to the side, and so on. So there is also another thing here that there is a heat flux defined boundary condition. So that means that there is a heat flux here, which is leaving the say over BC. So from starting from here to C, so we have a heat flux leaving the boundary, a defined value again, something like if you apply a flame here, okay, flame is actually input into the heat input into the body, but otherwise in general we show it that it is leaving the boundary here. So which we represent in the mathematical terms as, so heat leaving this one is given as, if you recall, here we have a minus K, and here we write it as dou phi by dou n. So what is n here? So n is an outer normal. So this is a normal vector to the boundary. Okay, so it's a normal vector to the boundary. So what essentially this is dou phi by dou n is nothing but derivative of the temperature in the direction of the normal n. So that together with minus K represents the heat leaving the body. I mean heat leaving the boundary in the direction of n. So this is heat flux leaving the boundary in the direction of n. Of course, obviously a negative sign because of the heat flows in the negative gradient of the temperature. So if this is also defined here, Qn, so this is a defined value. Okay, so this is a defined value. So this is another boundary condition where heat flux is defined to be, again I put a bar here which shows that this is a defined value. Interestingly, there is one more. So another boundary condition here is between the third part C to A. Again here also is heat is leaving the boundary here, but heat is leaving because there is a temperature phi here and a phi infinity. So this is phi hat is infinity and it's a far field temperature. Such as, so a part of this boundary is exposed to say something like air or a fluid medium, where the heat leaving this one depends upon the temperature of the surface of the body and the phi infinity, which is defined by the ambient temperature. Okay, so how much heat is leaving? So one part of this, how much is heat flux? So that means that this minus K dou phi by dou n, this is, so that means that if phi is the temperature of the surface, so phi and the derivative of this one in the direction of n at this point multiplied by K, so that will give you the heat flux moving out in the direction of n. So here this is n, right? And this is equal to h times. So this is called a convective boundary condition, wherein the part of the boundary is exposed to a fluid at a far field temperature by infinity, okay, ambient temperature. So this, how much heat is leaving this boundary depends upon the difference between this temperature of the surface and by infinity far field temperature. So the difference multiplied by the H. H is called convective coefficient. Convective coefficient. Okay, heat convective coefficient. So that way we have defined three types of boundary conditions here. One is on a temperature defined boundary condition, so which we call as gamma phi, on gamma phi. And then a second one is a heat flux boundary condition, so which we call as gamma q here. So BC is a heat flux boundary and which we call as gamma q. And then the third one, the part CA, is a convective boundary condition. So this is a gamma H on the third part here, C2A. Okay. So there are three types of boundary conditions. So depending upon what type of boundary conditions, so maybe there may be existence of only one or two, or there may be existence of all the three temperature, all the three types of boundary conditions. Okay. So this one is called a steady state heat conduction problem. This probably I could have mentioned it earlier also. Conduction problem, in the sense that phi is a function of phase, or if it is two dimensions, or it can even be x, y, z if it is a three-dimensional problem. Okay. On the other hand, there are other types of things, or unsteady state heat conduction problem. Heat conduction problem where phi can be a function of space as well as time t. Okay, so there is a time here. Time also comes into the picture. And then if the time comes, so then there may be another variable also that might come into this one. So in the sense that if the temperature keeps changing, so there is a possibility here that the material here may also store some part of the heat. So what we call here is that the material may have some specific heat depending upon the material, and then so which might absorb, which may not absorb. So it depends. So that also may come into the picture. So for the moment, we will constrain ourselves to a steady state heat conduction problem, and these are the governing. This is the governing equation, and these are the set of boundary conditions. So why we want to analyze the heat conduction more often in this course is that the phi, which is the temperature here, temperature as a function of xy, is only one variable. Of course, which we are going to talk about a little later about the solid mechanics problems, where the body is subjected to forces, and then if it is a two-dimensional body, then every point within the body will be governed by two displacements. Every particle in that one is going to undergo two displacements, u in the x direction u and in the y direction v. So there you have two variables. So we are going to handle those things also, but then for a little time. So we are going to take up this problem, okay, more often. And heat condition problem, where we understood the whole set of governing equation and boundary condition. On the other hand, this is, since we are talking about the Poisson's equation, such things can also be equally applied to other applications which we talked about. What is that? The membrane problem, or even flow problems, which we didn't really talk about, or even the torsion of non-circular cross sections. So I think at this moment we will stop at this point, and then we will take up the other type of posing the problems and the methods how to solve it. Okay, bye then.